By a normal space, we mean a topological space in which for every pair of disjoint closed sets, there are two disjoint open sets containing those closed sets. And we know that every normal T1 space is called a T4 space. In the last lecture, we have proved some properties of normal spaces. We have shown that the property of a topological space being normal is a topological property. That is, every homeomorphic image of a normal space is normal. But we have also seen that normality is not a hereditary property. That is, a subspace of a normal space need not be a normal space. Today we will continue the topic. We will prove some important results related to normal spaces. Now we will prove the theorem which states that every compact Hausdorff space is normal. Earlier we have shown that every compact Hausdorff space is regular, and now we will see that every compact Hausdorff space is normal also. Let us prove this theorem. Let Xt be a compact Hausdorff space, and to show that this is normal we need two disjoint closed sets. Let L and M be two disjoint closed sets in X. As every compact Hausdorff space is regular, we have proved this result earlier. So for each small l belongs to capital L, there exists two open sets GL and HL such that GL contains L, HL contains M, and GL and HL are disjoint. Then the collection GL, where L belongs to capital L, is an open cover of L, because for each L in capital L we have an open set. So this is an open cover of L. As we know that, and actually we have proved in the last semester, that every closed subset of a compact space is compact. And here, since L is a closed subset of compact space X, so L is a compact subset of X. Thus, this open cover is reducible to a finite subcover. So here we have finite number of sets GL1, GL2 up to GLN such that L is contained in union of these GL1, GL2 up to GLN. Since each GLI is an open set, so their union is also an open set. Let us denote this union by G, then this G is an open set. And if we take corresponding sets HL1, HL2 up to HLN, and we take intersection of these open sets, then and denote this by H, then this H is also an open set, because finite intersection of open sets is also an open set. So here we have two open sets G and H such that L is contained in G, and since each HLI contains M, so M is also contained in H. It remains to show that G and H are disjoint, so we take their intersection and we write union of GLI, I varies from 1 to n, intersection of HLI, I varies from 1 to n. Since intersection distributes over union, so here we can write GL1 intersection of HLI, union GL2 intersection of HLIs, like this. And in each bracket, since uh, uh, one of the HLI is disjoint from GLI, so here we get empty set. So each bracket here is empty, and union of empty sets is empty, so here we get empty set phi. Hence, Xt is normal. Now we note that as a compact Hausdorff space is T1, because Hausdorff space is nothing but a T2 space and T2 space is T1. So compact Hausdorff space is T1, and so it follows from the above theorem that every compact Hausdorff space is T4. Now the next theorem is every regular Lindelof space is normal. Recall that a Lindelof space is a topological space in which for every open cover there exists a countable open subcover. Let us prove this theorem. Let Xt be a regular Lindelof space, and we want to show that this is normal. To show that this is normal, we need two disjoint closed sets. Let L and M be disjoint T closed sets in X. We know that every closed subspace of a Lindelof space is Lindelof. We have proved this result in the first semester. And so, since here L and M are closed subsets, and so L together with subspace topology TL and M with subspace topology TM are Lindelof subspaces of Xt. Let L belongs to capital L, and since L and M are disjoint, so L belongs to complement of M, that is X minus M, where X minus M is T open. This is a T open set because M is a closed set, so its complement is open. Since L belongs to X minus M, so X minus M is a neighborhood of L. And this is a neighborhood of L, so there exists a neighborhood of L, and so there is a T open set GL such that L belongs to GL and closure of GL is contained in X minus M. But then we have GL closure intersection M is phi, because GL closure is contained in the complement of M, so GL closure doesn't contain any element of M. Then the collection C containing sets of the form GL intersection L, L belongs to L, is a TL open cover of L. Why this is TL open cover? Since GL is T open, so GL intersection L is an open set in the subspace topology on L. So these are open sets. GL intersection L is an open set in L, and so this is a TL open cover of L. As L is a Lindelof space, so there exists a countable subcollection Gn. N belongs to the set of natural numbers N of C, such that L is contained in union of Gn. N belongs to capital N. And because Lindelofness implies that there exists a countable subcollection, so we have some countable collection Gn such that L is contained in union of Gn. And then clearly Gn closure intersection M is phi, because here earlier we have seen that GL intersection L, GL closure intersection M is phi, so Gn closure intersection M is phi for every N belongs to M. And similarly, there exists a countable subcollection Hn, N belongs to N, of Tm open sets such that M is contained in union of Hn, N belongs to N, and Hn closure intersection L is phi for every N belongs to N. For each N in n, the set of natural numbers, we define Vn is equal to Gn minus union of Hi closer for all I less than or equal to n. And we define Wn is equal to Hn minus union of Gi closer where I is less than or equal to n. Then from the definition of Vn, we find that Vn intersection Hi closer is equal to phi for all I less than or equal to n, because Vn is obtained by removing Hi closures for I less than or equal to n. And from the definition of Wn, Wi is contained in Hi and Hi is contained in Hi closer. And so we can write Vn intersection Wi is phi for all I less than or equal to n. Similarly, from the definition of Wn, we can write Wj intersection Gn closer is phi for all n less than or equal to j. And since Vn is contained in Gn and Gn is contained in closure of Gn, so we can have Wj intersection Vn is equal to phi for all n less than or equal to j. So from these two results, we conclude that any Wk and any Vn are disjoint. So we can write Wk intersection Vn is phi for all k n in the set of natural numbers. From the definition of Vn, we have Vn is equal to Gn minus union of Hi closer where I is less than or equal to n. Then this can be written as Gn intersection complement of union of Hi closer I is less than or equal to n. And we know that finite union of closed sets is a closed set and its complement is open, and so Vn is intersection of two open sets, and so Vn is an open set for each n in the set of natural numbers n. Similarly, we can show that Wn is an open set for each n belongs to n. Let G is union of Vn n belongs to the set n of natural numbers, and H is equal to union of Wn where n belongs to the n set n of natural numbers. Then G and H are open sets. Why? Because they are union of open sets. So G and H are open sets as Hn closer intersection L is phi. In the last slide we have seen that Hn closer intersection L is phi for all n belongs to n. So from the definition of Vn, we can say that L is contained in Vn, because earlier we have shown that L is contained in union of Gn's. But since Hi closer does not contain any element of L, so L is contained in G. And similarly, we can say that M is contained in H. And since Vn and Wn are disjoint sets, so G intersection H is clearly empty set. And so we find that Xt is a normal space. Thank you.